Welcome to the online course on radiochemistry. This course focuses on the basics of radioactivity and radiochemical methods of analysis as applied to the drinking water analysis. The course is divided into 8 different modules. Generally, the modules should be taken in numerical order, as material in the first modules is referenced in later modules. The course will emphasize the basics of radioactivity, measurement of radioactivity using different analytical techniques, chemical separations as applied to radionuclide analyses, and quality assurance, quality control as applied to the radiochemical laboratory. The learning objectives for this module are: define the term activity and state the units for it. Define the term half-life. Understand the relationship between half-life and decay constant. Calculate the mass of a radionuclide based on its activity. Calculate the activity of a radionuclide in a sample either in the past or in the future. During each module in this course, the important points of the module will be highlighted with the following text box: key concepts. For this module, in Introduction to Radioactivity, the key concepts are: 1 Curie equals 3.7 times 10 to the 10th disintegrations per second. This is one of the fundamental units of measurement of radioactivity. dN dt, the rate of change of the number of atoms as a function of time, is equal to minus lambda times n. Lambda is known as the decay constant. Activity A equals lambda times n, and lambda, the decay constant, is equal to 0.693 divided by the half-life of the radionuclide. The weight of radionuclidic matter is an insignificant contributor to the overall mass of any environmental sample. What is radiation? Radiation as energy in the form of waves or moving particles emitted by an atom or other body as it changes from a higher energy state to a lower energy state. Radiation can be classified as ionizing or non-ionizing radiation, depending on its effect on atomic matter. The emitted particles may be charged or non-charged. The charged particles are directly ionizing as a result of Coulombic interactions, primarily, and via scattering, secondarily, with valence shell electrons of atoms. The non-charged particles are indirectly ionizing as a result of transfer of energy via momentum, where energy is acting as a particle versus acting as a wave. Non-ionizing radiation causes changes in bound electronic states of the atom. That is, any electron that is affected stayed with its original atom either by changing bound atomic orbital levels or by changing its spin state. Again, what is radioactivity? Radioactivity is a collection of unstable atoms that undergo spontaneous, random transformation, that is, radioactive decay, resulting in new elements or a lower energy state of the atoms. The IUPAC definition of radioactivity is nuclear decay in which particles or electromagnetic radiation are emitted or the nucleus undergoes spontaneous fission or electron capture. Activity is the shortened term commonly used for radioactivity. Activity is the number of atoms that decay per unit time. We will define activity in mathematical terms further on in this module. The units of radioactivity are defined several ways. The traditional unit is the Curie. 1 Curie abbreviated capital C, small I, is 3.7 times 10 to the 10th disintegrations per second. The International System of Units, or SI, unit for activity is the becquerel. 1 becquerel is 1 disintegration per second. Another commonly used unit is the disintegration per minute. As you can see, the key concepts on the right side of the slide has those units identified. These are terms that we'll be using frequently during the course of this module and subsequent modules. The physical characteristic associated with a radioactive material is the half-life. The definition of the half-life is the period of time it takes for the number of radioactive atoms to be reduced to 1/2 of its original amount. The mathematical symbol used to identify half-life is T sub 1/2. Each radioactive isotope has its own characteristic half-life. The graph displayed here shows the activity on the y-axis of 2 different radionuclides as a function of time in hours, where hours are displayed on the x-axis. The units of activity are picocuries, or 1 times 10 to the minus 12th curies. The graph is plotted as a linear function on each axis. Note that both lines are curved. The line for 228 actinium has a much more pronounced bend because it has a very short half-life, 6.1 hours. The 224 radium curve almost appears to be a straight line because of its much longer half-life compared to the range of the values on the x-axis. Note that one way to determine the half-life of a radionuclide could be graphically by plotting activity as done here and determining the time at which 1/2 the original activity remains. The plots shown here are the same as that in slide 8, except the y-axis is logarithmic scale and the x-axis is linear scale. This is referred to as a semi-log plot. When the activity of a pure radionuclide is plotted on a semi-log graph, it always shows as a straight line, as seen here for these 2 radionuclides. If the plot has any deviation from a straight line, there is a contribution to the total activity being measured from another radionuclide. When the activity of a radionuclide is observed over significant periods of time compared to its half-life, the activity decreases. Thus, the rate of change in the number of atoms from one small time period to the next will always decrease or have a negative value. This is true when we have a single radionuclide that we're observing. In the previous 2 plots, this is seen as a negative slope of the curves. The mathematical expression for this rate of change is dN dt equals minus lambda n. In other words, the rate of change of the number of atoms is equal to a constant times the number of radioactive atoms present at the time of measurement. The minus sign indicates that the rate of change in the number of atoms present is decreasing. That is, the radioactive atoms are decaying. The constant is called the decay constant, and it is specific for each radionuclide. The traditional symbol for the decay constant is the lowercase Greek letter lambda. The units for the decay constant are usually given in inverse seconds or inverse time units. We will see shortly how the value of the decay constant for a radionuclide is determined. This is referred to as the basic decay equation. The physical observation that we make to determine how much radioactivity a sample has is based on the number of decays that we count. So, although the rate of change in the number of atoms is negative, the observed counts are positive and are directly related to the number of radioactive atoms present in the sample at the time of the observation. Thus, the expression for observed activity is shown in the equation below. Activity equals plus lambda times n, the number of atoms at the time of the observation. This is a positive value as we are counting the number of decays that are occurring. If the rate of change equation for the number of atoms is integrated, we get the expression n equals n0 times e to the minus lambda t. This equation relates the number of radioactive atoms n at any time t to the number of radioactive atoms originally present, or n0. The letter e represents the Naperian exponential and has the value of approximately 2.72. This is similar to the base 10 value of 10. If we make a measurement of the number of atoms at time 0, n0, and then make another measurement when the number of atoms is 1/2 of n0, we can substitute into the equation and simplify. Note that the time period required to get to 1/2 the original number of radioactive atoms is called the half-life of the radionuclide. Traditionally, the half-life is designated by T sub 1/2. Go on to the next slide. If we take the natural logarithm of both sides of the equation and solve for lambda, we get lambda, the decay constant, equals 0.693 divided by the half-life of the radionuclide. Two key concepts have been presented here. The first is that the half-life is the time it takes for a group of radioactive atoms to decay to 1/2 of their original number. The second is that the decay constant is equal to 0.693 divided by the half-life. The decay constant can be expressed in any units of inverse time. However, you should be careful when performing calculations that time, t, and lambda always have the same units of time. For example, seconds and inverse seconds. This is a test yourself exercise. Use the concepts from the previous slide and calculate the decay constant for strontium-90 in units of inverse seconds. The half-life of strontium-90 is 28.8 years. Once you have performed the calculation, please go on to the next slide and check your results with the answer given there. Did you get lambda equals 7.6 times 10 to the minus 10th seconds? If not, please go back 2 slides, review the material, and then try the previous slide again. Another test yourself exercise, number 2. Here, we want to calculate the number of atoms of strontium that are present in 5.8 picocuries of strontium-90. And we also want to calculate what mass in grams of strontium this corresponds to. These calculations both involve the use of equations in previous slides. Calculate both these amounts and then check your results with the next slide. Solution to exercise number 2. How many atoms of strontium-90 are there in 5.8 picocuries of strontium-90? The key concept here is to remember that activity equals lambda times n. But first, we have to convert picocuries, the units of activity, into disintegrations per second. If we do that, we get 2.146 times 10 to the minus 1 disintegrations per second. Next, using the activity equation, activity equals lambda n, you can calculate the number of atoms of strontium-90. If we do that, you should have gotten 2.81 times 10 to the 8th atoms. If not, please go back and try to do this calculation again. The second part to exercise number 2 was to calculate the mass in grams of strontium given the amount of strontium-90 in the original problem. In order to calculate the mass in grams, we first have to convert the number of atoms to moles of strontium-90 by dividing the number of atoms by Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd atoms per mole. If we do this, we get 4.67 times 10 to the minus 16th moles of strontium-90. Knowing that grams of anything are equal to its molecular weight times the number of moles, if we multiply the molecular weight of strontium-90, 90 grams per mole, by the number of moles of strontium-90, 4.67 times 10 to the minus 16th, we get 4.2 times 10 to the minus 14 grams of strontium-90. Notice that this is an extremely small value, nothing that we could ever measure on an analytical balance. Thus far, we have discussed the concepts of radioactive decay. At this point, you should be 1. Comfortable with the concept of half-life. 2. Be able to calculate the decay constant for any radionuclide. And 3. Be able to calculate the mass of a radionuclide based on its activity. Now, let's consider the case where the decay product of a radionuclide is itself radioactive. How do you determine the activity of the parent? How do you determine the activity of the progeny? The number of atoms of the parent is decreasing, while the number of atoms of the progeny is simultaneously increasing from the decay of the parent and decreasing because of its own decay. When the progeny of a radionuclide is also radioactive, the progeny is decaying and being formed by the decay of the parent at the same time. Therefore, we have a different rate of change of atoms equation for the progeny. dN2 dt equals lambda 1 n1 minus lambda 2 n2. In this instance, the subscript 1 refers to the characteristics of the parent, and the subscript 2 refers to the characteristics of the progeny. When this differential equation is solved, we get the equation at the bottom of the slide. Using this equation, the number of atoms of progeny, N2, can be determined at any time t, knowing the number of parent atoms present at time 0, and the half-lives of the parent and the progeny. An important factor in this last equation is that the N20 e to the minus lambda 2t. If the parent radionuclide is made purified from all other radionuclides by careful chemical separation, the value of N20 is 0. This means that the job of the chemist performing chemical separations is extremely important. The determination of radioactivity can be made using one of four basic equations. The equation on the right in this slide is the fundamental method used. It uses the measurement of radioactive atoms decaying during the measurement period. Since no detector is 100% efficient, we must account for the efficiency of the detector in the denominator of the equation. It is important to note that the measurement period should be small compared to the half-life of the radionuclide, usually less than 5%. If it is not, a correction factor must be made for the decay of the radionuclide during the measurement interval. This slide shows the second of four equations. Equation 2 is used when we determine the number of decay events from a progeny and correlate it to how much parent was originally present. This occurs in both radium-226 and radium-228 analysis. Equation 2 can also be used to determine how many atoms of progeny will be formed after time t when the parent has been chemically purified. Remember that the final term N20 e to the minus lambda 2t is usually equal to 0 if the parent has been properly chemically purified. This would mean that N20, the progeny atoms, are equal to 0. This is the third of four equations. Equation 3 is used to determine the activity of a radionuclide at some time t after its original activity has been determined. Conversely, if we know the activity at time t, we can back calculate to find out the activity at time 0. This equation is derived from the equation on slide 12, n equals n0 e to the minus lambda t. If both sides of this equation are multiplied by lambda, we get activity. This is the fourth of the four equations. Equation 4 allows us to calculate the number of atoms of a radionuclide based on its activity when the activity is given in disintegrations per second. Conversely, we can also calculate the activity knowing the atoms of the radionuclide present. This is a test yourself exercise number 3. A radioactive source containing 3,000 picocuries of 137 cesium is 25 years old. Calculate how much activity it had when it was first made. The hint here is to use one of the previous four equations to solve this problem. The equation to use is A equals A0 e to the minus lambda t. In this case, we know the radionuclide, so we can calculate lambda. We were given the time between the two sample measurements. We know the activity that we finally have. We want to find the initial activity, A0. Simply substituting into the equation, we would get A0 equals 5,334 picocuries. If you did not get this answer, please try the calculation again. There are many analytical techniques for measuring elements: atomic absorption, inductively coupled plasma, gravimetric analysis, mass spectrometry. So why try to measure the decay particles for a radioactive nucleus to determine how much of the radionuclide is present? The answer is basically because the mass of radionuclides, particularly the amounts found in drinking water samples, are very, very, very small. If you recall back to the calculation we did for the mass of strontium-90, that amounted to approximately 10 to the minus 14th grams, a quantity so small it cannot be measured on an analytical balance, and it also cannot be measured by any of the traditional analytical techniques. The constituents of a sample are usually identified as major, minor, trace, and ultratrace in terms of their percent mass composition in the whole sample. For radionuclides in drinking water, the percent mass is even much smaller than ultratrace. This means that standard analytical techniques for measurement of elements will not work satisfactorily in detecting radionuclides. Overall, the weight of radionuclidic matter in these samples is an insignificant contributor to the overall mass of any of the drinking water samples that we would measure. The table shown here identifies the relationship between activity and mass of material. The relationship to take particular note of is that between half-life and mass for the same activity concentration. All of the radionuclides shown here have concentrations in water of 0.1 becquerels per liter. Now compare the half-life in years column with the atoms mass column. The atoms mass column represents the total atoms or mass of the radionuclide in the entire 1 liter of water. As the half-life increases, so does the mass present. However, we cannot measure on normal analytical balance any of these masses. The largest one is for 232 thorium, and that is 25 micrograms in the entire 1 liter of water. That's 0.025 milligrams. On an analytical balance, the smallest we can measure is 0.1 milligrams. This is the reason that radiochemical separations must be carefully performed. There is such a tiny mass of material that we're dealing with that even a little bit of sloppiness will result in major losses of our radionuclides. What kinds of radioactivity are there in the environment? Why should we need to measure radioactivity in drinking water if drinking water is supposed to be clean? There are two types of radionuclides, those that are naturally occurring and those that are anthropogenic, that is, made by man. This slide shows that of the naturally occurring radionuclides, there are two different groups. The first group is referred to as primordial, which means that they were formed when the Earth was formed some 5 billion years ago. Note that these radionuclides have half-lives in the hundreds of millions to billions of years. The second group is those radionuclides that are formed every day as a result of high-energy particle bombardment from the sun causing nuclear reactions with oxygen, nitrogen, and carbon in the upper atmosphere. The table shown here compares the maximum contaminant level, or MCL, of radionuclides as identified in Chapter 40 of the Code of Federal Regulations, with the concentrations of radionuclides found in rainwater and drinking water. The MCL is the limit of activity of these radionuclides in drinking water that is allowable. For an individual radionuclide, the MCL is determined based on an average person drinking 2 liters of water per day, and the radioactivity in that water from that single radionuclide yielding a maximum of 4 millirem dose in 1 year to the average person drinking that water. All of the radionuclides shown are naturally occurring radionuclides, with the exception of strontium-90. Strontium-90 is anthropogenic. Most of it in the environment is the result of atmospheric nuclear testing between the late 1940s and 1970s. This concludes our introduction to radioactivity. Based on what we have covered so far, you should be able to calculate the decay constant for any radionuclide based on its half-life, calculate the mass of a radionuclide based on its activity, and vice versa, calculate the amount of activity in a sample at some point in the past or future based on its current activity. Understand that when analyzing radionuclide contamination in water samples, we are attempting to measure really minute amounts of material. Please proceed on to the next module.